This mini lecture and example will illustrate the concept of the average value of a continuous function and how to calculate the integral that gives you the average value of a continuous function over a specific interval. Many people are familiar with the concept of an average value, typically relating to a set of discrete data, such that if you had a set of x values, that if you wanted to find the average x value using symbol very similar to the concept of centroid or center of mass, the average value is defined as the sum of all of the numbers in your data set divided by the number of data points in that data set. When you have a continuous function, though, you can't add up individual data points, or at least you can't add up individual data points in a practical way. You need some other method by which to calculate the average value. So when we look at a continuous function, so if I graph a typical continuous function, y equals f of x, if I am interested in finding what the average value is of this continuous function between the limits x equal a and x equal b, you'll notice that the value of the function on the left-hand side of the interval, if I substitute in x equal a into this general function, it's going to produce, in this case, the minimum value over that interval. If I go to the right-hand side, because this is a continually increasing function, if I substitute in on the right-hand interval into the function, I'm going to end up with, in this case, the maximum value of the function. And so the average value has to be somewhere between the minimum and the maximum. So the average value of this function is somewhere between the minimum value and the maximum value on the y-axis. In order to illustrate how one could find this, what we can do is we can break this interval into n pieces, just like a discrete data set. So if I break that up into n pieces, then I'm going to have a y0, a y1, a y2, all the way along until I have y to the n. So I'll have n plus 1 y values that I can add up and then divide by n in order to find out my total. So if I go from the left-hand side to the right-hand side here, my average value is going to be approximately equal to the sum from I equal 1 to n of all of my y values, but I divide by n. So that would be the definition of a discrete sum. In order to make the connection between this and integration, I'm just going to do a little trick here. I'm going to multiply both sides. I mean both numerator and denominator, not sides. Numerator and denominator by delta x, where delta x, if I break this up into n pieces, the width of each piece in the interval is going to be some change in x. So if I multiply both top and bottom of this equation by delta x, we have the numerator is the sum of the y values multiplied by the width of each piece. Now if you look, that ends up being the area of each little triangle. The area of each little triangle has a width of delta x and a height that is equal to the y value of the function at that location. So the total in the numerator is the total area of n rectangles. And the denominator, n times delta x, if I take each one of these delta x's and multiply them by n, it gives me the length of this entire interval from b to a. And if we, instead of doing this for a discrete number of data points, do this for an infinite number of data points, well, then the numerator becomes the total area via integration. So the average value is simply the area that is under the curve via integration over the interval divided by the interval width. Essentially, what this equation does is it gives you the value of a rectangle of some height that over that interval will underestimate the area and overestimate the area and two parts of the integral until it balances. It basically gives you the height of a rectangle that has the exact same area as the area under the curve over the same interval. So if we take the area calculation and divide by the interval width, we can calculate an average value. Here is an example. The average value of y equals 4 sine 3x between the limits of x equals 0 and x equals pi by 4. First step in any area problem, because average value is just an area problem, is to draw a picture. Now, 4 sine 3x is just a regular sine function, but it has a 3 in front of the variable x, so it's going to oscillate a little bit more quickly than a regular sine function, but it's still going to have an amplitude of 4. It starts at 0 here, there is no phase shift, and we're only going between 0 and pi by 4. Now, pi by 4, that's approximately, would be a 45 degree angle in degrees. If I multiply that by 3, I get 3 times 45 degrees, which is 135 degrees. So when I get from x equals 0 to x equals pi by 4 for the variable, the argument of this sine function only goes to 135 degrees. So it's going to go up, go past its maximum at 90 degrees and be on the way down on the other side at 135 degrees. So over this interval from x equals 0 to x equals pi by 4, we're going to try to find what the average value is of the function over this interval. Now clearly the answer has to be between y equals 0 and y equals 4. If you place your finger, this is very much like centers of mass. If I put my finger in the middle of the distribution, at the middle of the distribution between the minimum and the maximum, I'd end up with a value of something like y equal 2. But you'll notice that the function spends more time above 2 than it does below 2. So the average is likely to be higher than 2. And if I had to make a guess here, I would guess maybe it would be somewhere around this location. That's where it would balance on my finger. Maybe around 2.8, 2.9, maybe up as high as 3. In order to actually do the calculation, with an area question, you choose your rectangle is step number 2. If I pick vertical elements, the length of the rectangle is y minus 0, the y-coordinate of the curve minus 0, the y-coordinate minus 0, the y-coordinate minus 0, the y-coordinate minus 0, everywhere. There is no change, and so that's going to be the easiest way to do the problem. And so the area element dA is just going to be y times dx, or in this case, 4 sine 3x dx. And since the average value is, by definition, the area under a curve over an interval divided by the interval width, here, if we do y dx, 4 sine 3x dx is in the numerator. That is going to be the area element. When I integrate that, I'm going to get total area. And the integral will be from 0, minimum of x equals 0, to a maximum of x equal pi by 4. And it's going to be divided by pi by 4 minus 0. 4 divided by pi over 4, I can take those constants outside the integral and get 16 over pi. And then we only have to integrate sine 3x dx. Sine 3x dx, this is a standard form. The standard form on the table is sine x. Because of this linear factor of 3, you could do a substitution here. Let u equal 3x. du would be 3 times dx, but I only have a 1 dx here, so I'd end up dividing by 3. And essentially that's all you do. You write down the standard form here. The standard form solution for integral of sine of that angle would be negative cosine of the same angle, but I'm going to end up dividing by 3 because of that linear substitution. We evaluate this between the limits 0 and pi by 4. Evaluating at the upper limit of pi by 4, we end up with cosine 3 pi by 4, and I've factored out the negative third out front, and subtract the lower limit, evaluating at 0, that's cosine of 0. If you know your unit circle, cosine of 135 degrees, that's going to be negative 1 over root 2, so negative 0.707. Cosine of 0 is 1. And if I multiply this out, negative 0.707 minus 1 should be negative 1.707 approximately. Multiply by 16 over 3 pi negative, and I end up with average value 2.89807, and to 3 significant digits, this would be summarized as 2.90. And you can see that 2.90 is very similar to the guess that I made at the beginning. I knew the average would have to be higher than 2. I guess somewhere between 2.8, maybe up to 3. So that number has got to be correct.